All right, quantitative literacy. This is the 10.4 notes. We're actually looking at Pascal's triangle in this one. Now, this is just to show a neat trick that Pascal's triangle that we saw earlier in the semester can actually be used to do combination problems, not permutation, but combination problems. So I'm gonna, just on the first few problems that we're gonna look at here, I'm gonna show you how I could use Pascal's triangle to do this. It's just kind of neat, but on test, you'll just be using your calculator instead of the triangle either way, but it's kind of a cool little thing. So what's interesting is that if I read the entry in row in row N of number R, that actually tells me the number of combinations. So for example, if I had combinations of 5 choose 2, for example, I would go to row 5, that's the row. Now notice that the row does start with row 0. So I would go to row 5. Row 5, and it is entry number 2. That's the entry, but again, I start counting at 0. So this is entry 0, then 1, then 2. So it would actually be the number 10. So we're going to try this on the first few problems, but mainly this section is just doing some more problems with combination permutation stuff. So I'm going to just keep the triangle up for these first few problems, and I'll work on the left side here. So again, you should have the note packet. It is on. Don't want Cortana though. So for number 1, A through D, we have a committee of 4 that we're going to make. And we have 7 Democrats, and we have 3 Republicans that we can choose from for this committee of 4. So part A says we're going to pick exactly 1 Democrat. So for the Democrats, now this is going to be combinations because the committee just has 4 people in it. It doesn't matter what order they're in. It's just a committee. It's not a president, a vice president, all that stuff. So I have 7 Democrats to choose from, and I'm picking 1. And then for the Republicans, that means that, well, there's 3 to pick from. If it's a committee of 4 and I only picked 1 Democrat, I'm picking 3 Republicans. So I'm going to multiply these together. Now, again, you're going to do this on your calculator, but I just want to show you how this works using Pascal's triangle. For the 7 choose 1, I'm going to go to row 7 and then 0, 1. So actually the number 7 is the answer for the combinations of 7 choose 1. And for the Republicans, I'm going to go row 3 and over to 3. Again, I'm counting from the left, starting at the number 0. So 0, 1, 2, 3. That's actually just 1, which if you think about it, it makes sense. If I have 3 slots open and there's only 3 choices, there's only one way to pick that. Those 3 guys or girls. Excuse me, that was sexist there. So 7 times 1, 7. There's part A. For part B, I'm going to actually leave the first number in these the same because I'm still picking from the same group. But for part B, it's going to be 2 Democrats, which means if it's a committee of 4, I'm going to be picking 2 Republicans. So similar to what I did before, if I go to row 7 and count 0, 1, 2, there are 21 ways to do this. Combinations of 3 choose 2, 0, 1, 2. That number's 3, and that's going to give me 63. So just showing you that Pascal's triangle actually has this cool little thing with probability and counting and combinations and all that fun stuff embedded in it. All right, we're not going to use Pascal's triangle anymore. We're just going to keep doing the problems. And actually on this one, I'm just going to maximize this whiteboard, possibly. There we go. So for letter C, again, I'm leaving the 7 and the 3 on there. Now I'm choosing 3 Democrats. If it's a committee of 4, there's only going to be 1 Republican. This will be 35 times 3. Give me 105. And for the last part, D, go figure, it's going to be 4, which means 0 Republicans. This is part D. If I do 7, choose 4, there's 35 ways to do that. 3, choose nobody. There's only one way to do that. Don't pick anybody on the Republican side. That'll just be 35 times 1, 35. On number 2, your note said if 10 coins are 10 coins are tossed, how many ways are there of obtaining exactly 6 heads? It doesn't matter the order. I just wonder if I throw 10 coins, what are the chances, or sorry, how many ways are there of getting 6 heads total? So since order doesn't matter, it's combinations. Now you might be saying, well, aren't repetitions allowed because multiple heads? Each coin, think of it as its own separate heads and tails. So each heads and tails is different. So it is a combination. There are 10 coins, and I want 6 heads. So I just run that, and that would give me 210. For number 3, similar logic. It's a combination. This time there are 7 coins tossed. I want to get 3 tails. 7, choose 3, 35. And again, you could be using Pascal's triangle to do this, but obviously on your calculator it will be much faster. Number 4 now is a little bit tricky. We got to actually almost kind of think of this thing backwards. So Trish is on a game show. Get Trish up here. There's Trish. She has 9 boxes. She can't see that dollar sign. One of them has $1 million in it. She gets to pick 4 of the boxes. Now, how many selections of 4 boxes wins? We're going to do this in a very, feels almost backwards way. I'm actually going to think, okay, well, how many incorrect boxes are there? There are 8 incorrect boxes. If she's picking 4 boxes, she's going to pick incorrect boxes. But we don't want her to pick 4 incorrect boxes. We want her to only pick let's say that. Let's reword this. We'll say incorrect picks. Well, we don't want her to incorrectly pick 4. We want her to incorrectly pick 3. We know she's going to pick 3 incorrects if there's 1 correct. So what this really boils down to is it's combinations, because it's not saying the order matters at all, but all boxes are different, so it is a combination. She has 8 incorrect choices, but we only want her to incorrectly choose 3. This would give me all the ways she can pick 3 wrong boxes out of the 8 wrong showing, which by default would mean the 4th box would be the correct one. So for part A, it's 56. Now for part B, what is her probability of winning? This is kind of hinting towards what we're going to do in the final unit of the semester. Well, the total selections would be 9 boxes, and she's picking 4. So this is the grand total. We don't care about the $1 million or not. The total is 9 choose 4, which is 126. Probability is preferred outcomes, which is 56, over total outcomes, which is 126, which actually equals 0.4 repeating, which is actually 4/9, which makes sense. If there are 9 boxes and she gets to pick 4 of them, she's going to have a slightly less than a 50% chance of finding that right box in there. Okay, so that does it for the 10.4 notes, a fairly quick section, mainly just more practice.